Hey guys, this is Jay. We'll talk about mass spec, chemical equivalence, and proton NMR. I'll briefly talk about n+1 and n+2 peaks as it is not part of the worksheet. n+1 peak is caused by C13. On the periodic table, carbon has a molecular weight of 12.01. That is because in nature, 99% of carbon has a molecular weight of 12, and 1% of carbon has a molecular weight of 13. If there are more carbons in the structure, there's a higher chance that the structure has C13, which gives us the n+1 peak. Thus, the ratio of n to n+1 peak hints at the number of carbon atoms presented in the structure. Similarly, the molecular weight of chlorine and bromine are not whole numbers. They're averages of molecular weights of chlorine and bromine isotopes. Having a single chlorine will give us a 3:1 ratio of n+ to n+2 peak. And having a single bromine will yield us a 1:1 ratio of n+ to n+2 peak. In terms of proton NMR, chemical equivalence is important because it shows whether the hydrogens are exposed to the same chemical environment. We'll introduce three terms: homotopic, enantiotopic, and distereotopic. To test whether hydrogens are homotopic, enantiotopic, or distereotopic, we can replace each hydrogen with a heteroatom at a time and see the relationship of these different structures. If they're the same, then these hydrogens are homotopic. If they're enantiomers, then these hydrogens are enantiotopic. If they're distereomers, then they'll be considered distereotopic. Let's take this molecule labeled distereotopic, for example. So here, I replaced the dash hydrogen with a heteroatom on the left, and I replaced the wedge hydrogen with a heteroatom on the right. And the relationship of these two molecules are distereomers, meaning that these two hydrogens will be considered distereotopic. Note that in proton NMR, protons that are homotopic or enantiotopic will fall under the same signal. The number of signals in proton NMR equates to the number of unique hydrogen atoms in the molecule. For example, how many signals does this molecule have? It has a total of 2 signals because there are 2 unique hydrogens. Now we get to shielding and deshielding. Shielding hydrogens are associated with upfield, and deshielded hydrogens are associated with downfield. Note that upfield and downfield are relative terms. So a proton that is more shielded is upfield in relative to protons that are less shielded. To touch on the concept of shielding and deshielding, we need to come back to the general idea of how proton NMR works. So a magnetic field hits the atom, then we let it relax, and we measure its changes during the relaxations. So chemical shift reflects the magnitude of the magnetic field that is felt by that proton. So higher chemical shift means that the proton is feeling more of the magnetic field, and a lower chemical shift means that a less magnetic field is felt. Shielding is when electrons around the atom respond to the magnetic field and they generate their own magnetic field to oppose the applied magnetic field. So a shielded proton has more electron blocking magnetic field for that hydrogen, so that hydrogen is feeling less of the magnetic field. A deshielded proton will have less electron blocking magnetic field for that hydrogen, and more magnetic field is felt. An electronegative group such as halogen can pull electron density away, leaving less electron to block magnetic field for that hydrogen. So the hydrogen is deshielded and thus giving it a higher chemical shift because it's feeling more of the magnetic field. This diagram taken from Dr. Castleman's lecture further supports this idea. As you can see that the hydrogen nearby electronegative group has a higher chemical shift versus one that does not have an electronegative group nearby. Hope this helps, and thank you guys for listening.